this episode, we move from the broad idea of bash scripts being small programs into the more delicate mechanics that make scripts either predictable and safe or surprisingly fragile. Expansion and substitution are the behind-the-scenes behaviors that bash applies before it actually runs a command, and beginners often do not realize how much of the script's meaning is decided during this pre-execution phase. When a script behaves strangely, it is frequently because bash expanded something differently than the author expected, such as splitting a value into multiple pieces or interpreting special characters in a way that changes the command's arguments. That is why this topic matters for Linux Plus, because the exam does not only test that you recognize terms like variable and quoting, but that you can reason about why one script is safer than another and why one behaves consistently while another breaks on edge cases. We will build an intuitive mental model for variable expansion, for quoting and why it matters, for subshell behavior, and for command substitution, all at a level that helps you avoid common mistakes without turning this into a typing exercise. A useful starting point is to understand that bash reads and transforms your text before it runs anything, almost like a translator that first rewrites your script into a concrete set of arguments and then hands those arguments to programs. This matters because many beginners assume the shell passes your text exactly as written, but in reality, it performs expansions, substitutions, and splitting rules that can radically change what a program receives. Variable expansion replaces a variable name with its stored value. Command substitution replaces a special expression with the output of a command, and word splitting can then chop the resulting text into multiple arguments based on separators. Filename expansion can also turn patterns into lists of matching files, which is convenient when you intend it and risky when you do not. These transformations are powerful because they let a small amount of script text express flexible behavior. But the same power makes it easy to write something that works in a clean, simple case and fails in a messy real-world case. When you learn to think in two phases, the expansion phase and the execution phase, you gain a calmer way to predict what bash will do. Variables are the most common expansion feature, and at a conceptual level, a variable is simply a named placeholder for a value that the shell can reuse. That value might represent a directory, a file name, a username, a configuration choice, or a computed result, and the advantage is that you can change the value in one place and have the script adapt everywhere it uses it. The risk is that variables can contain unexpected characters, especially spaces, newlines, or wildcard characters, and the shell may treat those characters as meaningful separators or patterns during expansion. Another risk is that a variable might be empty because it was never set or because it was set incorrectly, and an empty value can cause a command to target something broader than intended. A beginner mistake is to treat variables as always safe text, but from the shell's perspective, variable content is just raw characters that will be interpreted by the expansion rules. When you treat variable values as potentially messy and unpredictable, you naturally adopt safer habits around quoting and validation. The environment matters here because not all variables originate inside your script, and that difference influences how much you should trust them. Some variables are set by your script, some are inherited from the parent environment, and some are provided by the system and used by many programs as shared signals. Inherited variables can be convenient, but they can also create hidden dependencies, where a script behaves differently depending on which session launched it or which user ran it. This is one reason consistent script structure encourages you to define important variables explicitly, so the script does not accidentally rely on a value that happens to be present on one machine but missing on another. It is also why many scripts treat certain environment variables carefully, because a changed environment can alter the meaning of file searches, language sorting, or which executables are found first. Even without naming every variable, you should understand the broader principle. Variables are inputs, and inputs should be treated as potentially unreliable unless you control them. That mindset makes your scripts more portable and more resilient to surprises. Quoting is the main tool for controlling how expansion results are interpreted, and the easiest way to understand quoting is to think of it as telling bash how to treat characters that would otherwise be separators or patterns. When you do not quote an expansion, bash may perform word splitting, which means it can break one value into multiple arguments at spaces or similar separators. That can change the meaning of a command, because a program might interpret multiple arguments differently than a single argument. And a file path with spaces is the classic example of this problem. Quoting can also prevent file name expansion from turning wildcard characters into lists of file names, which is important when you mint the character literally rather than as a pattern. Beginners often hear the advice to quote variables and treat it as a rule without reason. But the reason is that quoting preserves the value as one coherent unit, so it is passed to programs as intended. When you combine that with the earlier idea that the shell rewrites your text before execution, quoting becomes a way of shaping the rewrite so that the final arguments match your intention. It also helps to understand that not all quoting behaves the same, because different quoting forms influence whether expansions occur inside the quoted text. One common approach allows variable expansion while still protecting the expanded value from splitting and wildcard behavior, which is often what you want when inserting variable content into a command. Another approach treats almost everything inside as literal characters, which is useful when you need exact strings and do not want the shell to interpret variable markers or backslashes. This distinction matters because scripts often need both behaviors at different times, such as building a message that includes a variable value versus defining a literal pattern or configuration snippet. Beginners sometimes choose one quoting style everywhere and then become confused when variables do not expand or when characters are interpreted unexpectedly. The real skill is to choose quoting based on intent, asking whether you want the shell to substitute values or preserve literal text. If you can articulate that intent, you can usually predict which quoting behavior is appropriate without relying on memorized rules. Another concept that ties closely to quoting is how the shell splits words, and how that splitting can create subtle bugs that are hard to notice until the script is in production. Word splitting happens after certain expansions, and it can convert a single expanded value into multiple arguments, which may cause a program to read a file name as two file names or to treat part of a value as an option. This is especially dangerous when values can start with a dash, because a program might treat that as a flag instead of data, leading to unexpected behavior. A safe scripting mindset recognizes that variable content can come from file names, user input, or command output, and those sources can include whitespace and symbols that are meaningful to the shell. Quoting is a major defense, but so is being deliberate about how values are constructed and validated before use. If you imagine how messy real file names and real data can be, you will naturally become more cautious about unquoted expansions. That caution is not overkill, because many serious scripting incidents begin with a value that contained a space or a new line that nobody anticipated. Command substitution is another major source of surprise for beginners because it blurs the line between data and execution in a way that feels magical at first. Command substitution is the feature that lets you run a command and capture its output as text to be inserted into a larger command or assigned to a variable. The common syntax form uses the characters $sign followed by parentheses, and when Bash sees that, it runs the inside command and replaces the substitution expression with the output. The power here is obvious, because scripts can compute values dynamically, like detecting a system property or generating a timestamp like string, and then reuse that output in later decisions. The risk is that command output often includes trailing newlines or unexpected spaces, and once again, that output is just characters that may be split into multiple words if you are not careful about quoting. Another risk is performance and readability, because excessive command substitution can make scripts hard to follow and slow to run, especially if the same command is executed repeatedly. The safer mental model is that command substitution creates data, but that data must still be treated like any other input that might contain messy characters. Subshells are related but distinct, and they matter because they shape what state changes persist after a set of operations completes. A subshell is essentially a child shell process, and when you run a group of commands in a subshell context, variable changes, directory changes, and some other state changes occur in the child and then disappear when the child exits. This can be extremely useful when you want isolation, such as temporarily changing a working directory to perform operations and then returning to the original context automatically. It can also confuse beginners when they expect a variable assignment inside a subshell to still be present afterward in the parent shell. The key is to remember that processes are isolated, and a subshell is a separate process with its own copy of environment and variables, even though it begins by inheriting values. This is the same conceptual idea you already know from other Linux process behavior, but it becomes very practical in scripting because it determines whether your script state changes accumulate or remain contained. Once you see subshells as a containment tool, you can use them intentionally rather than stumbling into them accidentally. Understanding how subshells appear in scripts is important because you might create them without realizing it, and then wonder why a change did not persist. Some script constructs naturally spawn a separate process context, and that can mean a variable you set seems to vanish, even though it was set correctly in the moment. This is why script readability and structure matter, because when a script is clear about where isolation begins and ends, you are less likely to assume state will flow across boundaries when it will not. Subshells can also affect performance, because spawning extra processes has overhead, and in tight loops that overhead can become noticeable. Beginners sometimes learn to solve problems by wrapping logic in subshells without understanding the cost or the state implications, which can lead to scripts that are hard to reason about. A more mature approach is to use subshells when isolation is useful and to avoid them when you truly need state to persist. The exam-friendly takeaway is that subshells create a scope boundary for state, and scope boundaries are a major source of both bugs and safety when you understand them. Variable expansion and command substitution also interact with readability in a way that many beginners do not consider at first, because a script can become dense if every line contains multiple nested substitutions. When a reader sees layers of substitutions, they must mentally simulate the expansion order to understand what is really being executed, and that cognitive load increases the chance of missing a risky detail. Readability improves when you separate complex computations into named variables with clear purpose, because the script's logic then reads more like a narrative and less like a puzzle. This is not about avoiding powerful features, but about using them in ways that can be reviewed and maintained safely. In security and operations, review is a real control because a second set of eyes can catch an unsafe assumption before it becomes an outage. If your script uses command substitution to gather data, storing that data in clearly named variables can make the flow obvious and reduce repeated execution. The broader idea is that structure is how you manage complexity, and expansion features are inherently complex unless you present them clearly. A useful way to think about safe defaults in the context of expansion is to focus on the most common failure modes and design your script to minimize them. One common failure mode is an empty variable that expands to nothing and changes the scope of an operation, so scripts often check for required values before proceeding. Another failure mode is unexpected whitespace in variable content or command output, so scripts use quoting and careful parsing to preserve values as intended. Another failure mode is accidental pattern expansion, where wildcard characters and data are interpreted as file patterns, so scripts avoid letting untrusted values become unquoted command fragments. A further failure mode is assuming state changes persist when they occur in isolated contexts, such as subshells, so scripts explicitly manage scope and avoid relying on changes that will not survive. None of these ideas requires you to type commands while listening, because they are mental habits that shape how you write and read scripts. The exam often tests these habits indirectly by presenting two script snippets or two approaches and asking which is safer or more reliable. When you can identify these failure modes, you can select the approach that controls expansion behavior rather than being controlled by it. It is also important to distinguish between substitution that produces data and substitution that changes control flow, because scripts often blur the two. When you capture command output into a variable, you are turning runtime results into data that influences later decisions. When you rely on substitution inside conditional logic, you are letting the expansion phase shape what the condition evaluates. This is powerful, but it increases the importance of predictable output, because unexpected output can cause wrong branching decisions, and wrong branching decisions can cause incorrect actions. Beginners sometimes assume commands always output in a stable format, but many commands output differently depending on locale, environment, or error conditions, and that can make substitutions unreliable if you depend on formatting rather than on clear signals like exit status. A safer approach is to separate data gathering from decision making and to treat command output as something that can be empty, noisy, or error-prone unless you account for those possibilities. This is another place where readability and robustness align, because clear separation makes it easier to handle error cases without burying them inside nested substitutions. The more you treat substitutions as potentially messy inputs, the more resilient your script becomes. As you move toward exam readiness, it helps to unify these ideas into one consistent mental model you can apply to any script you read. Bash takes your script text, performs expansions like variable expansion and command substitution, then applies splitting and pattern rules, and only then executes programs with the resulting arguments. Quoting is the primary control you have for shaping that transformation so that values remain intact and patterns do not expand unexpectedly. Subshells introduce a process boundary that isolates state changes, which can be helpful for containment but confusing when persistence is expected. Command substitution is a way to turn a program's output into data, but that data can contain whitespace and new lines, which means it must be handled carefully to avoid surprising splits and misinterpretation. These concepts are not separate trivia items, because they are the source of many scripting bugs and many scripting security mistakes. When you can look at a script and predict how text will expand before execution, you are doing the kind of reasoning Linux Plus tries to measure. By the end of this episode, you should feel that expansion and substitution are not mysterious shell magic, but a predictable set of transformations that you can control once you respect how they work. Variables provide reusable named values, but their content can be messy, which means safe scripts treat variable expansion as something that should be protected by deliberate quoting and validation. Quoting is how you prevent Bash from splitting and pattern expanding your data into unintended arguments, which is why quoting choices often decide whether a script is robust or fragile. Command substitution provides dynamic values by replacing an expression with command output, but that output must be treated like untrusted input unless you control its format and handle whitespace carefully. Subshells create isolation by running commands in a separate process context, which is useful for containing temporary changes but can surprise you when you expect state to persist. If you carry this mental model forward, you will read scripts more confidently, write scripts with fewer edge case failures, and answer Linux Plus questions with stronger reasoning, because you will understand the hidden transformation phase that makes shell scripts behave the way they do.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.